quiet archive record. Tonight, we drift into the space beneath thought, where words slow down and silence begins to speak. Betelgeuse is one of the most famous stars in the night sky, not because it is the brightest, but because it is so unusual and so easy to find. It sits in the shoulder of the constellation Orion, a pattern many people learn early in life. For most stars, the story is simple. They shine steadily for millions or billions of years, and they look the same night after night. Betelgeuse is different. It is huge, swollen into a red supergiant near the end of its life. It changes brightness, it sheds gas and dust, and its surface is so large that modern telescopes can sometimes make out real structure, not just a point of light. Astronomers watch it because it is nearby in cosmic terms, because it is unstable, and because it offers a rare chance to study what massive stars do in their final stages. It is also a reminder that the sky is not frozen in place. Even a familiar star can be in motion, evolving right now. Tonight, we go through Betelgeuse, the red supergiant that could explode. Start with where it is. If you step outside on a winter night in the northern hemisphere, Orion is hard to miss. The pattern has 3 bright stars in a short, straight line. That is Orion's belt. Below the belt is a softer patch, the Orion Nebula, which can be seen, even with the naked eye, in dark skies as a small blur. Above and to the left is a bright star that often looks a little orange or red. That is Betelgeuse. In the southern hemisphere, Orion appears flipped, but the belt is still the key, and Betelgeuse still marks a shoulder of the hunter. The name itself comes from Arabic, filtered through many centuries of translation and spelling changes. Today, most English speakers say something like Betelgeuse, even though the spelling is odd. It has become a star with a kind of cultural life of its own, showing up in fiction, in star charts, and even as a reference point for people who do not follow astronomy. But the real reason it matters is physical. Betelgeuse is a red supergiant. That phrase sounds like a label, but it is an entire stage of stellar evolution. A star begins as a large cloud of gas and dust. Gravity pulls the cloud inward. As it collapses, the center gets hotter and denser until nuclear fusion begins. Hydrogen nuclei start merging into helium, releasing energy. That energy pushes outward while gravity pulls inward. For a long time, those forces balance. The star is stable. A star like the Sun can stay in that stable phase for around 10 billion years. Betelgeuse is not like the Sun. It was born much more massive. A massive star burns through its fuel far faster. It lives fast and it ends young. For Betelgeuse, the main story is that it is already past the simple hydrogen burning stage. When a massive star runs low on hydrogen in its core, the core contracts and heats up. Hydrogen fusion moves to a shell around the core. The outer layers expand. The surface cools. The star turns red. It becomes enormous. How enormous? Betelgeuse is so large that if you placed it at the center of our solar system, it would reach out past the orbit of Mars in some estimates, and in other estimates, it could approach Jupiter. The exact number depends on how you define the surface of a star that has a thick, fuzzy atmosphere. A red supergiant does not have a hard edge like a planet. The outer layers are extended and moving. Still, the scale is hard to grasp. The Sun is about 1.4 million kilometers across. Betelgeuse is hundreds of times wider. At the same time, It is not extremely heavy compared to the Sun in the way people might expect. Red supergiants have low average density. They are like giant, hot balloons made of gas. Betelgeuse likely has a mass somewhere around 10 to 20 times the Sun, depending on the model and the distance estimate used. That is huge, but not hundreds of times. The size is the dramatic part. The size is also why Betelgeuse can be studied in a special way. Most stars are so far away that even the largest telescopes see them as points. Betelgeuse is relatively close, and its disk is large enough on the sky that interferometers and specialized imaging can resolve it. Astronomers can see that its surface is not uniform. It has bright patches and darker regions. It has large convective cells, like boiling, where hot material rises and cooler material sinks, but on a scale that makes the Sun's granules look tiny. When you say surface for a star like Betelgeuse, you are talking about a layer where the gas becomes transparent enough for light to escape. That layer can shift. The star pulses. The atmosphere moves. Dust forms and is pushed outward. That leads to one of the key facts about Betelgeuse. It is losing mass. Red supergiants shed material into space. Their outer layers are not tightly bound. They can be pushed by radiation pressure, by pulsations, and by the chaotic motion of convection. Over time, a star like Betelgeuse can lose a large fraction of its mass before it dies. This matters because the star's final explosion, if it happens as a supernova, will expand into that surrounding material. The interaction between the blast and the previously ejected gas can shape what we see. Astronomers have observed complex structures around Betelgeuse. There are arcs, shells, and clumps of gas and dust. Some of this may come from older episodes of mass loss. Some may come from the star's motion through the interstellar medium, creating a bow shock like the wake in front of a boat. Infrared observations show dust, while radio observations reveal gas. Betelgeuse is also a variable star. That means its brightness changes over time. Many stars vary. Some vary because they are in binary systems and eclipse each other. Some vary because they pulsate. Betelgeuse is in the second category. It has multiple periods of variability. One is around a few hundred days, often described as roughly 400 days. There is also a longer secondary period that can be several years. These variations are not perfectly regular, like a metronome. They have scatter. They can drift. That is expected in a star with a dynamic, turbulent atmosphere. To understand the variability, imagine the star as a sphere of gas that is not still. It expands and contracts. When it expands, the surface cools and it can look redder and dimmer. When it contracts, it can heat up and brighten. On top of that, huge convective cells can create bright regions and darker regions, changing the total light output. Then there is dust. When material is blown off, it cools as it moves outward. In the right conditions, dust grains can form. Dust absorbs visible light and re-radiates in infrared. If a cloud of dust forms along our line of sight, Betelgeuse can appear dimmer in visible light, even if the star itself has not changed much. All of these ingredients came together in one event that made Betelgeuse a global story. In late 2019 and into early 2020, Betelgeuse dimmed dramatically. People who knew Orion well could see it. It was not gone, but it was much less impressive than usual. News stories spread fast. The phrase, "Betelgeuse is about to explode," appeared everywhere. Astronomers reacted in a more restrained way. A supernova is one possible end for a red supergiant, but soon, in astronomy, can mean many different things. Still, the dimming was striking. It was called the Great Dimming. What caused it? Several lines of evidence suggest it was a combination of normal pulsation plus a large dust event. One scenario is that a convection-driven outflow ejected a chunk of material from the surface. The gas cooled, dust formed, and that dust cloud partially blocked the star. Observations in different wavelengths supported this idea. Some imaging showed that one side of the star looked darker, as if something was obscuring it. When the dimming ended and Betelgeuse brightened again, it did not mean the star had returned to a stable state. It meant the dust had dispersed or moved, and the pulsation cycle continued. This is the first big lesson of Betelgeuse. It is not a static object. It is a changing system. Now move to the question everyone asks. How far away is it? Distance sounds basic, but it is one of the hardest numbers to pin down for Betelgeuse. For nearby stars, astronomers use parallax, the tiny shift of a star's apparent position, as Earth orbits the Sun. If you measure that shift precisely, you can compute the distance. Betelgeuse is bright, and its atmosphere is extended and uneven. That makes parallax measurement harder than for a clean, point-like star. Different methods and different data sets have produced different estimates. For a long time, a common number in popular sources was around 640 light-years. More recent studies have suggested it might be closer, perhaps around 500 light-years, or even somewhat less. The exact value matters, because it affects the star's inferred size and brightness. If it is farther, it must be more luminous to look as bright as it does from Earth. If it is closer, it can be less luminous. In professional astronomy, this is not just trivia. The star's luminosity is tied to its mass and its evolutionary stage. Distance uncertainty spreads into uncertainty about when it will reach core collapse. Even so, there is a strong, safe statement. Betelgeuse is close enough that it is one of the best red supergiants for study, and far enough that if it explodes, it will not harm Earth. That second part is worth stating clearly. A supernova within about 30 to 50 light-years could have serious effects on Earth's atmosphere. Betelgeuse is far beyond that. If it goes supernova, it will be a spectacular light show, possibly visible in daylight, but it will not be an extinction event. What would it look like? A red supergiant supernova would brighten rapidly, then fade over weeks and months. It would likely become one of the brightest objects in the sky, perhaps comparable to the full moon at peak in some estimates. Though exact brightness depends on distance and the details of the explosion, it would appear as a new bright point near Orion, changing the familiar pattern. It would also produce neutrinos, a flood of tiny particles that pass through matter easily. Neutrino detectors on Earth would likely see a burst. This would be a major moment for physics because neutrinos carry information directly from the collapsing core. It would produce gravitational waves as well, though whether current detectors would see them depends on the asymmetry and the distance. But the key question remains: when? The honest answer is that we do not know. Betelgeuse could collapse tomorrow in cosmic terms, or it could take tens of thousands of years. Astronomers can narrow down the stage by modeling its mass, luminosity, pulsation, and chemical signatures. They can look for evidence of what fuel is burning in the core, but they cannot see directly into the core. The outer atmosphere can tell you something, but it does not give you a countdown clock. Still, there are reasons Betelgeuse is considered a candidate for a relatively near-future supernova. One is simply that it is already a red supergiant, a short-lived stage for massive stars. Another is that its mass suggests it will not end as a quiet white dwarf. Stars like the Sun end by shedding outer layers and leaving a dense core called a white dwarf. Massive stars end by core collapse. In a core collapse supernova, the star builds heavier and heavier elements in its core. Hydrogen fuses into helium. Helium fuses into carbon and oxygen. Later stages can fuse carbon, neon, oxygen, and silicon. Each stage produces less energy per unit mass and runs faster. The final silicon burning stage can last only days. When the core becomes mostly iron, fusion can no longer produce energy. The core collapses. Betelgeuse is likely in the phase where it has already fused helium and is working through later stages, but the exact stage is debated. There are clues in surface chemistry because convection can bring fusion products up. There are also clues in the star's luminosity and temperature. Yet even if you know the stage, the time left can vary a lot. A star might spend hundreds of thousands of years as a red supergiant, or far less, depending on mass and rotation and mass loss. Rotation is another hidden factor. Many massive stars rotate rapidly. Rotation mixes material inside the star, changing how it evolves. Betelgeuse today is not spinning fast at the surface, but the core could have different behavior. Some models suggest it may have had a companion star in the past, or it may have merged with another star. That kind of event could change its rotation and its mass loss history. There is also the question of whether Betelgeuse will explode as a red supergiant, or whether it might evolve back toward a hotter, bluer state before core collapse. Some massive stars move back and forth on the Hertzsprung-Russell diagram, depending on internal changes and mass loss. Betelgeuse seems firmly red today, but long-term evolution is complex. What we can do is treat Betelgeuse as a case study in how astronomers learn about stars. The tools are diverse. There is simple, naked-eye monitoring, where amateurs record brightness changes over years. There is spectroscopy, where light is split into colors to reveal chemical lines. The lines can tell you temperature, surface gravity, and motion. There is high-resolution imaging and interferometry, combining light from multiple telescopes to effectively build a much larger telescope. There are infrared observations that track dust. There are radio observations that track gas. All of that builds a layered picture. Betelgeuse is a star with an extended atmosphere. Above the photosphere, there is a chromosphere, and beyond that, a wind. In the wind, molecules can form. Dust can form. The wind carries material away. The wind is not smooth, it is clumpy. That clumpiness matters because it affects how mass loss proceeds, and mass loss affects the star's future. If a star loses enough mass, it may end differently. It may produce a different type of supernova. It may leave behind a neutron star or a black hole, depending on the final core mass. This leads to another interesting fact. Betelgeuse may leave behind a neutron star. A neutron star is an incredibly dense object, about the mass of the Sun compressed into a sphere about 20 kilometers across. It forms when the collapsing core rebounds and the outer layers are blasted away, leaving the core supported by neutron pressure. If the core is too massive, it may collapse into a black hole instead. Where Betelgeuse falls depends on its initial mass, how much mass it has lost, and how the explosion proceeds. Some models suggest Betelgeuse is in the range that could produce a neutron star, but uncertainty remains. Another fact is that Betelgeuse is not a single, isolated object in a perfect vacuum. It moves through space relative to the local gas. That motion, combined with its wind, creates a bow shock, detected in infrared. The bow shock is like the star plowing through thin interstellar material, piling it up. The structures around the star show a history of outflow. If you could see in infrared and radio with your own eyes, you would not see an empty region around Betelgeuse. You would see a messy environment shaped by the star itself. Now return to the surface. The surface of Betelgeuse has been directly imaged in a limited way. It is not like a planet image, but it is still extraordinary. You can see bright areas that are likely hotter upwelling gas. You can see darker regions. These are thought to be giant convection cells. On the Sun, convection cells at the surface are small compared to the Sun's disk, and there are many of them. On a red supergiant, the cells can be huge, perhaps a significant fraction of the star's radius. That can lead to large, localized outflows. These outflows can seed dust formation. So when Betelgeuse dims, it might not be a single global contraction. It could be a combination of pulsation plus one large plume of material that makes dust. Betelgeuse is also a star with a complex set of periodicities. The shorter period, around 400 days, is often associated with radial pulsation, where the star expands and contracts. The longer period, sometimes called the long secondary period, might be related to giant convection patterns or cycles in mass loss. The star can also have irregular behavior. This is not a clock. It is weather. If you watch it long enough, you see patterns, but also surprises. Astronomers have tried to model Betelgeuse in detail. They use stellar evolution codes, adjusting parameters like mass, metallicity, rotation, and mass loss to match observed luminosity and temperature. They use pulsation models to match observed periods. They use radiative transfer models to understand how light moves through the atmosphere and through dust. They compare models to observations across the electromagnetic spectrum. This process is slow, but Betelgeuse keeps rewarding it because it is close, bright, and active. Another interesting fact is how bright Betelgeuse really is. In intrinsic terms, it is far more luminous than the Sun. The Sun's luminosity is about 3.26 watts. Betelgeuse is tens of thousands to perhaps over 100,000 times more luminous than the Sun, depending on the distance. Yet its surface temperature is lower. This is because luminosity depends on both temperature and surface area. Betelgeuse has a huge surface area. Even if each square meter emits less light than the Sun's surface, the total output is enormous. The star's color is also part of its identity. It is often described as reddish or orange. In reality, the exact color perception depends on sky conditions and how your eyes adapt. Many people see it as orange rather than deep red. But compared to the bluish stars in Orion, it stands out. That contrast is a reminder that stars have different temperatures. Blue stars are hotter. Red stars are cooler. Betelgeuse is cool for a star, but still extremely hot by everyday standards, with a surface temperature of roughly 3,500 Kelvin. Now consider scale again, but in a different way. If Betelgeuse replaced the Sun, the inner planets would be inside the star. Mercury would be gone, Venus would be gone, Earth would be gone. Mars would likely be inside the extended atmosphere, but the star's mass is only around 10 to 20 suns, so the gravitational pull at a given distance is not as insane as the size suggests. Still, the effect would be catastrophic for the inner system. This is why red supergiants are sometimes described as stars that have become huge and soft. They are large, but not dense, and they are unstable. One more important piece is what Betelgeuse tells us about the life cycle of elements. Massive stars are factories. They fuse light elements into heavier elements. When they explode, they spread those elements into space. Later generations of stars and planets form from that enriched material. In that sense, a star like Betelgeuse is part of the reason rocky planets and life can exist. Elements like oxygen, carbon, silicon, and iron are built and distributed through massive star evolution and supernova explosions. If Betelgeuse explodes, it will seed its region of the galaxy with heavy elements. But even before it explodes, it is already enriching space through its wind. The dust it produces becomes part of the interstellar medium. In time, that dust can become part of new star systems. Now step back and look at the human side. Betelgeuse has been watched for centuries. Its variability was noticed long ago. In the 1800s, astronomers recorded changes. Even before that, some have suggested ancient observers may have noticed changes, though that is hard to prove. In the modern era, amateur astronomers and variable star organizations track it with systematic measurements. This is one of the ways astronomy stays connected to human observation. Even with space telescopes, a bright nearby star still benefits from many eyes. Now look at the Great Dimming again. It showed how quickly a scientific story can spread. It also showed how astronomy handles uncertainty. When the dimming began, astronomers did not announce a supernova. They gathered data. They compared wavelengths. They built models. Over time, the dust explanation gained strong support. The public story often stayed stuck on the explosion idea because it is dramatic. But the real story, the dust and outflow and pulsation, is also dramatic. It is just more detailed. The Great Dimming also led to new observations. New high-resolution images were taken. New spectroscopy was done. More attention was focused on the star. In that sense, Betelgeuse became a live laboratory, and it remains one. Now go deeper into what a red supergiant really is. A star like Betelgeuse is not just big. It is in a phase where its internal structure has become layered. In the simplest picture, hydrogen fusion happens in the core at the start of a star's life. When the core hydrogen is used up, the core is mostly helium. Gravity squeezes it. The temperature rises. Hydrogen fusion shifts into a shell around the core. The outer layers swell. That swelling is what turns a star into a giant. In a massive star, the chain continues. Once the core gets hot enough, helium fusion begins. Helium nuclei fuse into carbon and oxygen. Later, if the star is massive enough, the core can burn carbon, then neon, then oxygen, then silicon. Each stage happens at higher temperature and for a shorter time. The endpoint is iron. Iron is special because fusing iron does not release energy. It costs energy. So once the core becomes rich in iron, the star has reached a wall. The internal engine that supports it cannot keep going the same way. This is why massive stars end in core collapse. But Betelgeuse is not at the final seconds, at least as far as we can tell. It is in the red supergiant phase, which could still last a long time. Long here might mean tens of thousands of years, not millions. To place Betelgeuse on the standard map of stars, astronomers use a diagram that plots luminosity against temperature. It is called the Hertzsprung-Russell diagram. Hot stars are on one side, cool stars are on the other. Bright stars are high, dim stars are low. Betelgeuse sits on the upper right. It is cool but extremely bright. That upper right region is where red supergiants live. In classification terms, Betelgeuse is usually described as a red supergiant of spectral type, around M1 to M2, with a luminosity class of I. That means it is in the supergiant category, not a normal giant. The spectral type tells you about temperature. An M-type star is cool enough that molecules can exist in its atmosphere. You can see molecular absorption bands in its spectrum. The luminosity class tells you that the star has low surface gravity and is very extended. You can also learn about motion. In spectra, absorption lines can shift back and forth due to the Doppler effect. In a star like Betelgeuse, some line shifts trace pulsations and flows in the atmosphere. Different layers can move at different speeds. This helps confirm that the atmosphere is not a quiet shell. It is a moving, layered, changing region. Betelgeuse also has what astronomers sometimes call a mole sphere, meaning a region above the photosphere where molecules exist and where conditions are complex. It is not a single smooth layer. It is shaped by shocks, flows, and local heating. If you are used to thinking of stars as simple balls of plasma, Betelgeuse breaks that habit. It has an extended, structured environment. This is part of why distance is hard. When you measure parallax, you are measuring the position of a point on the sky. But Betelgeuse is not a point. Its photocenter, the effective center of light, can shift as bright patches appear on the surface, or as dust forms around it. So even a high-quality space mission can struggle with it. In the last decade, large surveys like Gaia have transformed distance measurements for many stars. For Betelgeuse, the situation is more complicated. The star is very bright. It can saturate detectors. Its extended atmosphere and variable surface make the centroid less stable. This can introduce systematic errors. So astronomers combine methods. They use interferometry to measure angular diameter. They use spectroscopy and models to estimate effective temperature. They use brightness and extinction estimates. They use radio measurements of masers in the surrounding gas when available, because maser spots can give parallax too. The result is a range of plausible distances, with the current best estimates clustered in a band rather than a single exact number. Even when distance is uncertain, some facts remain solid. Betelgeuse is close enough to be resolved. Betelgeuse is luminous enough to be a supergiant. Betelgeuse is in a late phase of stellar life. Now consider its brightness in the sky. Astronomers measure brightness using magnitudes. Smaller or negative numbers are brighter. Betelgeuse is usually around magnitude 0.4 or 0.5 when it is in a typical state, but it can vary. During the Great Dimming, it dropped to around magnitude 1.6 in some reports, meaning it became several times dimmer in visible light. This change is visible to the eye when you compare it to nearby stars. In Orion, a useful comparison is Rigel, the blue-white star at Orion's opposite corner. Rigel is usually brighter than Betelgeuse. When Betelgeuse dims strongly, the contrast becomes dramatic. Another comparison is Aldebaran in Taurus, another reddish star. Betelgeuse can look similar or brighter depending on the phase. These simple comparisons are part of why Betelgeuse is a good target for long-term monitoring. Now ask a different question. What does the surface look like? When astronomers make images of Betelgeuse with interferometry, they often see a bright region and a dimmer region, and sometimes more complex patterns. These are not small spots like sunspots. They can cover a huge fraction of the disk. The likely cause is convection. Convection is how energy moves in the outer layers of many stars. Hot gas rises. As it rises, it expands and cools. Cooler gas sinks. This creates cells. On the Sun, you see this as granulation. On Betelgeuse, the scale is enormous. The physics is similar, but the parameters are different. Lower surface gravity, larger scale height, different opacity, and strong pulsations. So the surface can be dominated by a small number of giant cells. These cells can be unstable. They can drive mass loss. A plume can rise, cool, and push material outward. Then dust can form, and that dust can block light. So the star can change its appearance and brightness. This connects the surface to the environment. If you observe Betelgeuse in the infrared, you see emission from dust and warm gas. If you observe it in the radio, you can trace molecular lines from the outflowing material. If you observe it in visible light, you see the photosphere and chromosphere effects. All of these layers are linked. Now talk about mass loss in more concrete terms. Astronomers estimate mass loss rates for red supergiants using models and observations of their winds and dust. Typical numbers for Betelgeuse are on the order of 1/1,000,000th of a solar mass per year, give or take, with uncertainty. 1/1,000,000th of a solar mass per year sounds small, but over tens of thousands of years, it becomes significant. It can shape the fate of the star. It can also shape what the supernova looks like, because the blast wave runs into that material. Some supernovae show strong interaction with dense surrounding gas. They are classified differently, and they can be brighter or have unusual spectra. Whether Betelgeuse will do that depends on its mass loss history in the final years, which is hard to predict. Now consider the star's motion. Betelgeuse is not sitting still relative to the gas between the stars. It moves through the local interstellar medium. When a strong stellar wind meets that medium, it can create a bow shock. In infrared maps, this bow shock can show up as an arc of emission ahead of the star's motion. It is a large-scale structure that says something about both the wind and the local environment. So Betelgeuse is not only a star, it is a system with a bubble of influence. Now move to the supernova. When a red supergiant collapses, the first thing that happens deep inside is rapid core contraction. As the core collapses, it releases gravitational energy. Most of that energy goes into neutrinos. A small fraction drives a shockwave. That shockwave moves outward. When it reaches the surface, there is a brief event called shock breakout. Shock breakout can produce a burst of ultraviolet and X-ray light that lasts minutes to hours, depending on the star. For a red supergiant, the star is huge, so the breakout can be spread out compared to a compact star. After breakout, the visible light rises. For a typical red supergiant supernova, the light curve can show a plateau, staying bright for weeks. This is why many red supergiant supernovae are called Type 2P, where P stands for plateau. The plateau happens because hydrogen in the expanding envelope recombines and releases energy, keeping the brightness up. There are also type 2L supernovae, where the brightness declines more steadily. Which type Betelgeuse would produce depends on the structure of its envelope and how much hydrogen remains. Now think about what the sky would look like. Betelgeuse sits near a region of the sky that many people recognize. A new bright light there would be noticed quickly. It might be visible in daylight at peak. It might cast shadows at night, but it would not be a sharp disk like the moon. It would still look like a bright point. The brightness would change over days and weeks. It would slowly fade. After the visible light fades, the remnant would continue to expand. Over years, astronomers would watch the debris and the interaction with surrounding gas. Over longer times, if a neutron star remains, it might become a pulsar, emitting beams of radio waves. Whether we could detect that depends on the beam direction and the surrounding material. Now step into the question of timing again. Astronomers can estimate how close a star is to core collapse by placing it in models and seeing what internal stages match the observed properties. But there is no direct probe of the core. So statements like Betelgeuse will explode soon are usually shorthand for Betelgeuse is in a phase where it could explode in the next tens of thousands of years. That is short compared to the star's total lifespan. To a human, it is not short. So the best way to think about it is that Betelgeuse is a rare chance. It is one of the nearest massive stars in a late stage. If it collapses in our lifetime, it will be a major scientific event. If it does not, it is still valuable, because it teaches us how stars approach the end. Now consider what a star like Betelgeuse has already done with its life. It formed from a cloud of gas that already had heavy elements. Those heavy elements tell you it formed after earlier generations of stars enriched the galaxy. It then spent millions of years fusing hydrogen. That phase might have lasted only around 10 million years or so, depending on mass. Then it expanded. Now it is in a state where the envelope is huge. The star is shedding material. The core is evolving. In this sense, Betelgeuse is a bridge between two kinds of astronomy. It is stellar evolution, which happens on huge timescales, and it is time domain astronomy, which tracks changes over days and years. Betelgeuse sits right in the overlap. Now shift to how astronomers measure size. One method is angular diameter. You measure how wide the star appears on the sky in milliarc seconds. Then you multiply by distance. The angular size of Betelgeuse is large enough that it can be measured, and it changes with wavelength, because different wavelengths probe different depths in the atmosphere. In some bands, you see deeper. In others, you see higher layers. So the star can appear larger or smaller, depending on how you look. This is another reason that the idea of a single fixed radius is an approximation. Still, it is fair to say that Betelgeuse is among the largest known stars by radius. There are other stars that may be larger, but many of them are farther and harder to measure. Betelgeuse is one of the best measured. Now talk about the chemistry you can see. In the spectrum, you can detect elements and molecules. You see signatures of molecules like titanium oxide, common in cool star atmospheres. You can also detect signs of processed material, like changes in carbon and nitrogen ratios, which can indicate mixing. These measurements help confirm that the star has gone through advanced stages, because mixing can bring products of fusion up to the surface. Now revisit the name. The name Betelgeuse is often explained as coming from a phrase that has been interpreted as the hand of the giant in Arabic, but the historical path is messy. It passed through medieval star catalogues and spelling shifted. What matters is that it is an old name. People have been naming and mapping the sky for a long time. And in that long tradition, Betelgeuse has become one of the most familiar, massive stars. Now return to the idea of measurement. When astronomers publish values for Betelgeuse, you often see ranges and error bars. This can confuse people who expect science to give a single number. But the error bars are the point. They tell you where the uncertainty is. For Betelgeuse, uncertainty is tied to distance, to the definition of radius, to the effect of a changing surface, and to the effect of circumstellar dust. When you see a statement like, Betelgeuse is 700 times the sun's radius, you should understand it as a representative estimate, not a rigid fact. What is rigid is the category. It is a red supergiant. It is huge. It is losing mass. It is variable. It is in a late stage. Now add detail to the variability because it is not one simple cycle. Betelgeuse is often described as a semi-regular variable. That means it has repeating patterns, but they are not perfectly steady. One prominent cycle is roughly a little over a year. Another is several years. On top of that, there is irregular noise from the changing surface. When astronomers plot the brightness over time, they can fit sinusoids and periods, but the fit is never perfect. This is expected. A red supergiant is not a rigid oscillator. It is a fluid body. Its outer layers respond to multiple drivers. Pulsation changes the radius and temperature. Convection changes the surface brightness pattern. Dust formation can block light, and mass loss events can add sudden changes. So the light curve is a blend. This is important when you hear dramatic claims. If the star becomes dim or bright, the first assumption should be that it is doing what variable red supergiants do. A supernova is a separate category. It would not be a smooth change. It would be a sharp, explosive rise. The Great Dimming was large, but it was not an explosion. It was a change that unfolded over months and then reversed. That is what winds and dust can do. Now talk about dust again, but with the basic physics. Dust grains form when the gas is cool enough and dense enough. In hot regions close to the photosphere, dust is destroyed, so dust tends to form farther out. But in a star like Betelgeuse, there can be cooler pockets and outflows that let dust form closer than you might expect. Once dust exists, it changes what you see. It absorbs and scatters visible light. It emits in infrared. So if you look only with your eyes, you might think the star has faded. If you look in infrared, you might see that energy has shifted. This is why multi-wavelength observations matter. Now move to a common point of confusion. Betelgeuse is sometimes called one of the biggest stars in the universe. In one sense, it is huge. In another sense, it is not uniquely huge. There are stars with larger estimated radii, but those stars are often far away, and their sizes are harder to measure precisely. Betelgeuse is one of the biggest stars that we can measure in detail. It is one of the biggest stars that feels close. It is one of the biggest stars that is part of the shared human sky. That is what makes it special. Now move to what happens after the explosion, because the afterlife is also part of the story. After core collapse, the outer layers expand at thousands of kilometers per second. The gas cools as it expands. Over time, it forms a supernova remnant. In a remnant, you can see filaments of gas. You can see shock waves. You can see regions where the blast runs into earlier mass loss. If the explosion leaves a neutron star, that neutron star can power additional emission. If it is a pulsar, it can create a pulsar wind nebula. If it becomes a black hole, the story is different, but the remnant still exists. In any case, the region around Betelgeuse would change. It would become one of the nearest laboratories for supernova remnant physics. Now return to what we know about the present state. Betelgeuse is often estimated to be around 10 million years old. That is extremely young compared to the Sun. It formed recently in galactic terms. It has burned through its core fuel quickly. This gives you a sense of how violent massive star evolution is. It is a fast path through the life cycle. Now consider how much energy Betelgeuse outputs. If you could collect the energy from the star at the distance of Earth from the Sun, the intensity would be far higher than sunlight. But of course, the star is far away. By the time its light spreads out across the sphere of space, only a small part reaches Earth. This is why it looks like a point. Distance turns enormous power into a small brightness. Now bring in one more modern observation tool: spectropolarimetry. By measuring polarization, astronomers can learn about scattering in the atmosphere and in surrounding dust. They can also learn about magnetic fields. Magnetic fields in red supergiants are not like the Sun's, but they can exist. They can affect mass loss in subtle ways. Betelgeuse is not usually thought of as a magnetic star, but magnetic fields can still be part of the picture. Now add a section on how Betelgeuse compares to the Sun, because that is one of the easiest ways to feel the scale. The Sun is a stable main sequence star. Its brightness changes only slightly. It has a defined radius. It has a strong, consistent structure. Betelgeuse is the opposite. It has an atmosphere that is a large fraction of its radius. It pulses. It sheds mass. It has large surface cells. It is close to its final fate. If the Sun were a basketball, Betelgeuse would be a stadium. But the stadium would be filled with thin fog, not solid walls. That image gets at the low density. Now talk about density in plain terms. The average density of Betelgeuse is far lower than air at sea level. Even if the exact number depends on the radius estimate, the concept is stable. It is a huge volume with relatively modest mass, so its outer layers are weakly bound. That makes mass loss easier. Now return to the idea of a static camera view, but in the sky itself. If you watch Betelgeuse night after night, it does not move much relative to Orion. But in space, it is moving. It has its own proper motion. Over thousands of years, the pattern changes. This matters if you think of constellations as fixed. They are not. Now add a short section on what professionals would do on the day of a Betelgeuse supernova. Optical surveys would pick it up immediately. Robotic telescopes would begin monitoring. Spectra would be taken to classify it. Space telescopes would target it in ultraviolet and X-ray. Radio arrays would look for early emission. Neutrino alerts would be shared quickly. Scientists would compare the event to models of red supergiant explosions. They would also compare it to other nearby supernovae in history. The last supernova, visible in the Milky Way with the naked eye, was in 1604, Kepler's supernova, and before that, in 1572, Tycho's supernova. Those were not red supergiants. A Betelgeuse event would be different, and it would happen in an era with detectors of every kind. Now bring the story back to what makes Betelgeuse meaningful, even without an explosion. It is a reminder that stars are not permanent. The night sky looks stable because human lives are short. But stars are evolving. Some are evolving quickly. Betelgeuse is one of the few where we can watch the signs. Pulsation, mass loss, dust, surface structure, brightness changes. These are not distant theories. They are changes you can see. Now draw one more line between Betelgeuse and the larger universe. Massive stars like this one are common drivers of galactic change. They produce winds, they produce ionizing radiation, they explode, they shape star formation by compressing gas, they enrich the galaxy with heavy elements, they leave behind neutron stars and black holes. So a single star can affect its region for millions of years. Betelgeuse is a local example of that. Now finish with a grounded closing that does not promise a date. Betelgeuse is a red supergiant in Orion. It is huge. It is close enough to study in detail. It is variable. It is losing mass. It is in a late stage of stellar evolution. It will end in core collapse. We cannot predict the year. We can predict the outcome. And while we wait, we can learn from what it does now. Because even before the explosion, the star is active. Its surface boils in slow, massive patterns. Its light rises and falls. Its wind carries material into space. Its dust drifts outward. Its bow shock marks its motion through the galaxy. And above all, it stays visible. A bright orange star, a shoulder of Orion, a giant close to the end. There are also some specific numbers that help fix Betelgeuse in the mind. Astronomers often quote an angular diameter for Betelgeuse of roughly a few dozen milliarcseconds, commonly around 50 milliarcseconds in some measurements, depending on wavelength and method. A milliarcsecond is a tiny angle. It is 1,000th of an arcsecond, and an arcsecond is 1/3600th of a degree, so this is an extremely small apparent size. Yet it is large for a star. It is one reason interferometers can resolve it. If you combine that angular size with a distance of a few hundred light years, you get a radius that is hundreds of times the sun. Some estimates cluster around about 700 to 900 solar radii. Some go higher, some go lower. The details depend on which distance and which definition of radius you use, but all the estimates point to the same category. It is a red supergiant of enormous size. Luminosity estimates likewise vary. Because luminosity depends strongly on distance, the uncertainty in distance becomes uncertainty in luminosity. Still, typical values are tens of thousands of times the sun's luminosity. You can state it plainly. Betelgeuse puts out the energy of a small cluster of suns. Its surface is cooler, but its area is massive. Now add one more simple measurement that people can picture: surface temperature. A typical estimate for Betelgeuse is around 3,500 Kelvin, though it can vary and different layers can give different values. That is cooler than the sun, which is about 5,800 Kelvin at the photosphere. Cooler means the peak of the spectrum shifts toward red and infrared. That is why it looks orange. Now look at the star's spectrum again. Because it is cool, molecules can survive. Titanium oxide bands are common in M-type stars. These bands help classify the star. They also show how the atmosphere is layered and not uniform. Now consider how astronomers estimate mass. You cannot put a star on a scale. Mass is inferred from models. You take the observed luminosity, temperature, and evolutionary stage. You find which models match. For Betelgeuse, The inferred mass is often in the range of about 10 to 20 solar masses. That range is wide, but even the lower end is far above the Sun, and it is above the threshold where the star will end in core collapse. Now consider radius and mass together. A star that large with that mass must be low density. That is why the atmosphere can be loose. That is why the wind can carry material off. Now add a detail about how the wind is driven. For hot stars, winds can be driven strongly by radiation pressure on atoms and ions. For cool red supergiants, the mechanism is less direct. Pulsation can lift material, convection can push plumes upward, dust can form, and then radiation pressure on dust can help push it outward. So the wind is a combined process. That is part of why it is clumpy. Now add a detail about how Betelgeuse has been studied in the modern era. In the 20th century, variable star observers built long records. In the late 20th and early 21st, interferometry improved. Arrays like the Very Large Telescope Interferometer and others have produced higher resolution views. Radio telescopes have mapped molecules in the environment. Infrared telescopes have mapped dust. Space missions have provided large-scale survey data. Betelgeuse has benefited from all of it. Now add a point about why astronomers want to connect a known star to a known supernova. For most supernovae in other galaxies, you see the explosion, and only afterward do you search old images to find the progenitor. Sometimes you find it. Often you do not. When you do, you have only a rough sense of the star. Betelgeuse is different. We can study it before the event. We can map its atmosphere. We can track its variability. We can measure its environment. So if it explodes, it becomes a benchmark. It becomes a reference point for the whole field. Now add one more clear statement about risk. Because it is far away, the main hazard is not radiation damage. The main effect is brightness. It could be bright enough to draw attention. It could affect night sky observations for a while. It could become an object of constant news. But it is not a threat. Now return one last time to the human experience. If you want to find Betelgeuse, you do not need a telescope. You find Orion, you find the belt. Then you look to one shoulder. You see the orange star. Then you remember that it is not a simple point. It is an enormous, evolving object. A star with a changing surface. A star with an outflow. A star surrounded by its own dust. A star that has already changed in visible ways. And a star that will not last much longer in cosmic time. That is why it remains one of the most interesting stars in the sky. It is close. It is huge. It is late. It is active. And it is easy to find. One more layer of detail is how Betelgeuse fits into the modern idea of time-domain astronomy. In the past, astronomy was often about mapping and cataloguing. Today, a large part of it is about change. Telescopes scan the sky repeatedly. They watch for new points of light. They watch for stars that brighten or fade. They watch for explosions, flares, and pulses. Betelgeuse is a nearby training ground for this way of thinking. It is not an explosive transient yet, but it is a variable object that teaches observers what real stellar change looks like. When a star dims, the first job is to ask what wavelengths change. If only visible light drops but infrared rises, dust is a strong suspect. If the spectrum changes in a way that implies temperature change, pulsation could be involved. If the line profiles shift, motion in the atmosphere can be part of it. During the Great Dimming, teams did all of these checks. They monitored photometry. They took spectra. They imaged the star with high resolution. They compared the data with past cycles. This is how a dramatic headline becomes a measured conclusion. Betelgeuse also shows the limits of precision. Even with the best instruments, the star is messy. Its surface is not uniform. Its environment is not uniform. Its brightness is not stable. So a perfect model is hard. Instead, astronomers build families of models. They compare which ones match best. They update them as new data arrives. That is the realistic way science works on a complex target. Now add a detail about the speed of change in late-stage massive stars. Early in a star's life, changes are slow. A main sequence star does not change much year to year. Late in life, the interior changes faster. The burning stages become shorter. The structure becomes more unstable. The envelope responds. So the variability you see is not just noise. It is connected to the stage. This is why red supergiants are watched. They are late enough that they show activity. They are not so late that they are gone. Now add a final practical fact for people who want to look. Betelgeuse is easiest to see when Orion is prominent, which depends on the season and your latitude. In mid-northern latitudes, Orion is a winter constellation. In summer, it is near the sun and hard to see at night. When it returns to the night sky, you can compare Betelgeuse to the other bright stars nearby. You can notice if it looks bright or dim. You can see if it looks more orange or more pale. These are simple observations, yet they connect you to a real process. A giant star changing on a scale that humans can notice. Now bring the story to its final idea. Even if Betelgeuse does not explode for 10,000 years, it has already done something rare. It has made a large part of the world pay attention to a single star. It has reminded people that the sky is not just a background. It is full of objects with lifetimes and endings. And in that sense, Betelgeuse is already a kind of warning, not of danger, but of time. The most familiar patterns above us are built from stars that will not last. One of them is already close to the end. A red supergiant in Orion. A star that can dim in plain sight. A star that sheds its own atmosphere. A star that will become a supernova. And until that day comes, it stays where it has always been, in the human sky. A bright shoulder of Orion. Betelgeuse. There is also a simple way to understand why a star like Betelgeuse becomes a supergiant in the first place. As fusion proceeds, the core composition changes. When hydrogen becomes helium, the mean molecular weight increases. The core contracts. Contraction raises temperature. That change forces the star to adjust. Energy generation moves outward into shells. The envelope responds by expanding. When the envelope expands, the surface cools. Cooler surface means redder light, so the star becomes large and red. At the same time, because the star is luminous, radiation and convection both play major roles in moving energy. The balance of those processes shapes the atmosphere. In a star like Betelgeuse, the atmosphere becomes a place where physics that is normally hidden becomes visible. You can see the signature of molecules. You can see the signature of dust. You can see changes in brightness that track real structural motion. It is not just a remote light source. It is a physical object with features and layers. This is why Betelgeuse shows up so often in discussions of stellar death. It is one of the clearest examples that you can point to in the real sky. It looks like a single star, but it is a system in transition. And because it is close, the transition is not just theoretical. It is measured, it is watched, it is recorded, it is ongoing. If you wanted to summarize the star in a few lines of plain facts, they would be these. Betelgeuse is a red supergiant in Orion. It is one of the nearest massive stars in a late stage. Its radius is hundreds of times the sun. Its luminosity is tens of thousands of suns. Its surface temperature is a few thousand Kelvin, which makes it look orange. Its brightness changes over months and years. It sheds gas and dust, building a complex environment around itself. It may collapse in the next tens of thousands of years, or it may last longer. If it collapses, it will become a bright supernova in a familiar part of the sky. None of these lines require perfect numbers. They are the stable shape of the story, and they are enough to explain why astronomers keep returning to this star. Because it is close, because it is huge, because it is active, and because it is near the end of a massive star's path. And there is one more reason Betelgeuse is worth attention. It shows that even the biggest objects can behave in ways that look almost like weather. Bright patches form and fade, outflows rise and thin, dust appears and drifts, the star pulses, its light changes. None of that is a countdown clock, but all of it is evidence that the star is alive in a physical sense, still converting fuel, still moving energy outward, still reshaping itself as the core evolves. So when you look at it, you are not looking at a static icon. You are looking at a process, a massive star nearing its last chapters. If the star never did anything dramatic again, it would still be one of the best nearby examples of how massive stars age. If it does explode, it will link decades of observation to one sharp event. Either way, the value is the same. A clear, close look at a red supergiant near the end. For now, it remains what it has been for human eyes for a long time. A bright, orange marker in Orion. A reminder that the universe changes, even when it looks still. This was a quiet archive story, where the story ends, sleep begins,